Hey, my name's Yusuf, and today we'll be looking at Lab 5, Choose Your Own Adventure, and I chose Gyroscopic Precession. The main purpose of this lab is to study the motion of a gyroscope as it is spun and placed on a fixed point. We aim to compare the experimental motion captured in a video with a glow script computational model that simulates that gyroscope's motion under ideal conditions. Our goal is to determine how closely the computational model predicts the behavior of the real gyroscope, and then to analyze what exactly causes this behavior. The system is modeled using principles of rotational dynamics such as the right-hand rule, torque, and angular momentum. By analyzing the motion using a glow script model, we can predict how the motion of the gyroscope and examine how that model's predictions align with the real behavior. So here's a preview of the main results. The computational model predicts that instead of falling down, the spinning gyroscope will start rotating in the XY plane along its point of contact with the floor, demonstrating an interesting physics concept referred to as gyroscopic precession. The model was consistent with the experimental model as shown in the video demonstration. However, over time, the real gyroscope begins to deviate from the ideal motion due to unmodeled forces such as friction and air resistance. The gyroscope's falling motion can be attributed to the magnitude of torque that's being exerted by gravity overpowering the angular momentum as its spin slows down. So look more into what this exactly looks like. Here's the experiment itself. The system was a gyroscope and the surroundings were the table and the earth. So as the rope is tied around the gyroscope's inner axle and pulled such that the inner wheel has a large angular velocity, as you can see down here, the bottom of the gyroscope is then placed on a stand at an angle that is very slightly over the horizontal, so almost perfectly perpendicular. The gyroscope was then let go and its motion was observed. So we tried to predict this motion using a computational model in GlowScript. Over here we set the mass of the apparatus, then we set the radius of the wheel, then we set the axle length, so that's the distance between the pivot and the center of the wheel. Here we set the moment of inertia of the wheel, and then we set the wheel's angular velocity, the force due to gravity, and pivot height, which is just the location that we want to put the pivot at. So that's like the base of the gyroscope itself. Then we set up the scene with the title, the width, height, and whatever, and then we place the pivot in that vector based off of the height that we declared. Then we create the axle, which is a cylinder, and the wheel, which is a ring. Then we create our visual arrows to let us visualize the angular momentum of the gyroscope at any given moment, and the torque that is exerted by gravity at any given moment. So this will be shown in red, and this will be shown in green. Then we'll calculate that initial angular momentum, that initial torque, as follows. Then we declare the time, so it's going to start at time 0, and then we'll record data every 0.01 seconds. So down here in our loop, which occurs based off of that time interval, we will update our torque first by using the cross product of that distance and then the force. And then down here, we will adjust our angular momentum by multiplying that torque value by the delta t, so the change in time. And then over here, this is our axle precession. So we're just keeping our orientation of our axle in the same direction that we calculated our angular momentum to be at. So that will make sure everything is visually there. And then here we're just spinning the wheel. So this is just declaring how our wheel will be spinning based off of the angular velocity. Then we'll keep the wheel aligned with the axle. So we're just attaching these two things together to make sure that they match. And then we're updating our angular momentum and torque visuals so that we can visualize how those two values are changing as we progress through our model. So what does this model look like? Well, it looks something like this, and we can actually see it if I run GlowScript. So as you can see, this disk over here is spinning, and this is our pivot point. So as this spins, gravity is exerting a torque in this direction. Because if we use the right-hand rule, we know that the moment arm is acting this way, and then the force of gravity is acting this way. So that makes that in the direction that's perpendicular to that. So this is gravity. And then we know from the right-hand rule that our angular momentum is coming this way. So that results in this motion over here, and we'll be discussing this more shortly. And here's our actually observed motion, which is taken from a video.
Yes.
So as you can see, it's spinning in a way similar to our computational model, though it's starting to fall off as it keeps on going. And we'll see why this happens and why this motion as a whole happens. So let's discuss. Why do they move like this? Though the observed gyroscope eventually falls down, both the model and the observed gyroscope start spinning around the point at which they make contact with the stand. So wherever that pivot point is, they both start spinning around that point. Why is this? Well, from the right-hand rule, we know that the angular momentum points in this direction. Then if we take r cross f, we know that the torque from gravity acts in this direction. So as these two values are always perpendicular, all this torque is doing from gravity, all that's doing is changing the direction of angular momentum. So it's incrementally moving the angular momentum here, then here, then here, then here, then here, and all around. So all this torque, all this force of gravity is doing is it's shifting this position that our angular momentum vector is at. So the main reason that the two models differ is that the computational model does not account for friction, and the real spinning gyroscope, as friction acts on the pivot point and through air resistance, the angular momentum of the gyroscope decreases over time. Initially, the torque from gravity causes the gyroscope's angular momentum to change direction, resulting in precessional motion. However, as angular momentum decreases due to friction, the torque from gravity no longer effectively changes the direction of angular momentum. Instead, the torque increasingly causes the gyroscope to tilt downward. This shift occurs because the magnitude of angular momentum becomes too small to sustain horizontal precession. As a result, the gyroscope's axis begins to drop and eventually falls over rather than continuing to precess. And here are conclusion questions. What if the gyroscope spins at a higher speed? Well, if the gyroscope were spun faster, its initial angular momentum would be greater, which would result in a higher speed of precession. The gyroscope would start precessing more quickly because the rate of change of angular momentum is directly related to the torque applied by gravity. With more angular momentum, it would resist changes to its orientation more effectively, so it would sustain this precession for a longer time. What does it mean for the direction of angular momentum to change without its magnitude changing? Well, if the gyroscope resists falling because of its angular momentum, which creates a stabilizing effect, the torque from gravity, instead of causing the gyroscope to tip over, redirects the angular momentum over and over, resulting in this precession. The resistance to tipping demonstrates how rotational motion can maintain stability in dynamic systems. This shows that stability in rotational systems in general isn't about remaining motionless, it's more about redirecting the forces in a way that prevents collapse. The gyroscope's motion is a form of dynamic equilibrium rather than static equilibrium, where gravity and angular momentum are constantly shifting. Thank you.